Here we are at the Sietsma Farm Feeds Mill in Howard City, Michigan. Feed mill, storage bins, dryers, and the biomass facility. We have the system separated into two different rooms. We have the feed room, which also houses the rotary gasifier. The Sietsma Farms rotary is 9 foot in diameter by 60 foot long. We're currently running on wood chips. We're in the process of installing the wet electrostatic precipitator that will allow us to run back on turkey litter. At Sietsma, we use a simple drag chain conveyor on the floor. It's pulled along slowly through a gate. The knife gate is adjustable if we need to increase our rate dramatically. The floor conveyor is also on a variable frequency drive, so we can control it from the HMI. From the floor conveyor, we transition onto an incline belt conveyor. The incline belt conveyor is a single-speed conveyor. Serves nothing more than transportation from the feed floor conveyor up to the weigh belt conveyor. The weigh belt system is a fairly standard belt conveyor unit, retrofitted with Siemens components, load cells, and control system to constantly track our throughput across the weigh belt. The weigh belt is also on a VFD, so we can control the pile height and get the best or most accurate measurements possible. From the weigh belt, we transition into a triple dump airlock. The triple dump allows us redundancy. We always have two gates closed at any given time, maximizing our airlock. Triple dump drops directly into, at Sietsma here, we have a 12-inch stainless steel screw feeder. The auger and associated trough inside is all stainless steel for temperature purposes. That's also on a variable frequency drive, so we can control the feed rate in, keep the screw as covered as possible to help protect it. Here at the feed hood, we have a fly ash removal system for any dropout as the gases entrain small particles and make the turn to go out of the feed hood. Anything that's dropped out is taken away with another stainless screw. Simple transition into a standard stainless auger into a double dump, and they just have a storage vessel that they change out every couple days. So onto the kiln. Feed hood, everything was designed by HTI. Into our syngas outlet duct, which goes over into the other room. Feed hood is brick lined. We use both insulating fire bricks and hard bricks for abrasion. The kiln was repurposed from Spokane, Washington. Used to be a couple 100 feet long. We cut it into sections, shipped it back, and put it back together for our purposes. Our air control system allows us to put air only underneath the pile where it will do the most work, reduces tramp air into the system, helps us maintain temperatures and reactions. The drive system is pretty standard for a rotary kiln. We've got a diesel backup here. That's an option, or we could do an inching drive with a generator or a PTO drive. Continuing with the drive system, standard pinion and girth gear drive, spring plates, welded solid to the shell, heavy duty pin connection on the girth gear. These are fabricated by Morbark to our design. Second air plenum. We can run as few as one and as many as 3 air plenums, depending on the size of the kiln and the process. Ash hood into ash transition. Same construction as the feed hood. Very similar in size, shape, support structure. 2 layers of brick insulation, a soft insulating brick and a harder hot surface brick. From that transition, we travel up a water-cooled auger through another set of double dumps, airlocks, and then out a secondary conveyor, which takes it out to a storage bin. The trunnion roller assembly is fairly standard beam or box frame construction. Here we use FL Schmidt bearings. They're water-cooled, sleeve-type bearing. They run in an oil bath. Most new systems will have a tapered roller bearing style. More cost-effective, less maintenance, and they're more forgiving on setup. They can take a little bit more misalignment. These have to be perfectly aligned. Still a good, solid bearing. They've been used for a long time. Now we'll head back over to the power side and take a look at the thermal oxidizer. So here's where the syngas ductwork continues through the wall to the power generation side. Again, the ductwork is simple construction, rolled, flanged with refractory lining into the cyclone. Cyclone separator pulls out the fines that do make it through the ductwork. From the cyclone, travel back up and out of the top into our transfer duct. We have an eductor burner on here to ignite when necessary. When we're at steady state, all burners are turned off and we keep our temperatures high enough for auto ignition. So by adding in oxygen through these pipes, we begin combustion of the syngas. Travel into the oxidizer. We start a swirling mixing motion as it travels down. The plenums you see here, the 2 donuts, are secondary air where we complete combustion and add a slight amount of tempering air to make sure we have full combustion. Out of the thermal oxidizer, we go through a simple duct into a boiler. We have a large ceramic isolation valve, motor controlled, so it's accurate and driven up and down. We don't rely on gravity. Very dependable design. Boiler, simple fire tube boiler, transition in. As I said, simple standard off-the-shelf boiler. Bought a package from the back end of the boiler. We've got our stack ducts coming out through our induced draft fan, where it's then forced out of the stack. For future poultry litter jobs, at this point we would go directly into the wet electrostatic precipitator. We are in the process of our cut-in right now, installing one at the Seatsma feed facility. Here's the position of the existing stack. For the west cut-in, the duct would exit through the south wall of the building, through the existing ID fan, then into the WESP. All exhaust would then exit through the WESP stack.